operated by the Edison. Edison is a very famous company and they are operated this power plant. So they guide us that this power plant is working underutilization from due to the Ukraine-Russia war and some high prices of gas, because this is working with the methane gas. So when we reached there, so I just observed that the wind was blowing very superb at this site. So when we came back, I discussed with my professor that we need to work some kind of wind plant with the integration of this plant. So I started working on this project from last year December. So today we have first there is a very short story about that, what is the policy and market context about this research. So as you know that this year, not this year, from last 10 to 15 years, there is a progressive heat wave in across Europe. So due to heat wave and some other factors, Russia-Ukraine factor, renewable energy resources area is very growing. So in Europe, everyone is talking about the renewable energy resources. So European Union also has a target that by 2030, the greenhouse gases should be reduced by 55% as compared to the 1990. And another directive that is issued by the EU, it is that by 2030 there should be at least 42.5% by the renewable energy resources. So all these factors encourage us that we should work on the renewable energy resources and somehow the integration with the renewable energy resources with the existing power plants. So this is the main our site that where the actual power plant is located. This is the Bussi, Sultrino, and the combined cycle gas turbine capacity is 120. This is a combined cycle. So I just want to tell you that the 100 megawatt is the main that is operated by the methane gas, and 20 megawatt turbine it is somehow by the residual gassing by using the combined cycle. So this is the total 25 kilometer area of this town, and this is the major area of this town is very beautiful, and this is under the Italian National Park. So we need to also focus on this, that how we can design the wind power plant by impacting minimum on our environment. So at very near to the existing power plant there was only 2 to 3 kilometers area that is under the Edison company. So we by just targeting this area we need to decided a 20 megawatt power plant. Okay, in next slide this is a just kind of our simulation that this can be the figure about the our wind turbine with the gas turbine. So when we have decided that we should work on the power plant, we have decided the site. The next task was how we can, what are the parameters that we should focus on by designing a wind power plant. So main thing is the mean wind speed. So we calculated the mean wind speed. This is around 7.86 meter per second. This is very good mean speed amount using the 6 to 9. This is the mean wind speed is considered very good for the wind power plant, and the power density is 467 at the site, and the V-will shape parameter around 2.10. So I just want to talk about the V-will shape parameter. Basically this is a parameter used to check the variability on different fields. We can use this in mechanicals for the variability of the wind. So when we have checked all these parameters, then we decided to check the whole year wind speed at this site. So we divide the whole year into 4: winter, spring, summer and autumn, into 4 months period for each. So for the winter period, the mean wind speed is 9.1 meter per second, which is very awesome for a wind speed, very good for a wind power plant. And power density at that time is 487 watt per meter square. So this is the basic time when we need a lot of electricity in the context of Italian national grid, because the weather is very cold and we need some extra electricity for a heating purpose. Okay, so this month are very good. Then the spring, the mean wind speed is 7.6. This is also a good. Then for the summer, June to August, this period our mean wind speed is somehow 5.6 meter per second. And at that time, this is we can install, but this is not a good time for a wind speed. So we calculated for the whole year. So this is the our main wheel speed distribution and turbine power curve at the site. We using the MATLAB we calculate this. So when we have decided all these parameters, when we have decided the our site, then next task, how can we design for a wind power plant? So we decided, as I have told earlier that to you, that we have decided that we need to design a wind power plant around 20 megawatt by considering the close area near to the combined cycle gas power plant. So this is the the design of the wind turbine. So where we decided to choose a 3 megawatt, and its 92 is the diameter of the turbine, and the number of turbines are 7. So the total calculation tell us that this power plant can be a 21 megawatt. So by using the MATLAB, we use these equations to simulate this, and this is our simulation of the wind turbine with different parameters, and this is the output of this wind turbine. So at this slide, this is telling us that I have already told you, in the month of winter our wind speed is very good for a wind turbine. So at that time we are using the maximum capacity of the wind power plant. But at that time there is a less, we are using the very less capacity of the combined cycle gas turbine. So this slide is telling us about our different monthly, you can say that winter 447 is the power density, and we are using the less combined cycle gas turbine is the 30%. So this is based on the our annual mean speed parameter like that. So this is also the elaboration of the previous slide. So now this is I am talking about the techno-economic analysis. So when we talk about the techno-economic analysis, we just need to compare with the already published study. So we compare with two studies in our paper. So one is already installed this kind of power plant in Italy, but this is not located with the combined cycle. This is an onshore wind power plant. So by using this kind of topology, that we are going to install a power plant with our already existing combined cycle gas turbine, so our effective capital cost is reduced about 18%, and there is a levelized cost of electricity euro 2082. This is our Italian, you can see that euro currency is used for the euro. So this is the techno-economic analysis and the key result. So in this table you can see that total installed capacity is 21 megawatt, and our net annual energy, this is 42.51 gigawatt per year, and our benchmark cost is the cost set by the ARENA. ARENA is the Italian electricity regulator framework, and we need to follow when we install to some kind of power plant in the context of the Italian. So this is the another slide where we use that our main total capacity that I was telling to the comparison with different studies. So in second table in 3 column you can see this is the Capracota site, this is in Italy, and at 4 this is the ECRES, Greece. So 25 megawatt wind plant is installed at Capracota, and ECRES, this is in Greece. So we compare our cost, our annual energy, and our payback period, and all these parameters we do with these two power plants to compare that our solution is cost effective, it is working or not. So this slide is about the environmental impact assessment. Obviously, when we are using the wind, so somehow we are reducing the CO2 emissions. So this is 9,905 ton CO2 displaced every year, and we calculated this value with the Italian grid value. So Italian grid value is 0.233 ton CO2 per megawatt hour. So in this slide you can see that annually how much CO2 we are reducing. So here are the challenges, mitigation strategies and BES pathways. So here I want to tell you that I already have told you that this power plant is at a site where there is a most of land is under the national park of Abruzzo region of Italy. So we also need to consider that we need to design our power plant in a way that it should be minimum environmental impact on the site. So these are the key findings and contributions that I have told you, that site viability confirmed that there are the parameters about in first section 7.8. These are the parameters we will and another. So for the power plant we use the double feed induction generator turbines, and these are the values that we are already I have discussed with you. And the in third time there is a techno-economic analysis of the sites. So thank you so much, and at the end of this I want to also thank to the Edison company by providing opportunity to work with them, and I am happily to share that I think so almost 2 weeks ago we have a meeting with the Edison company, and they were very sure that this project will be on site maybe at the end of this year or at the start of next year, because they have the some very initial approval by the competent authority of the Italian government. So thank you so much.
Questions?
Any questions?
Yes. Why don't you take an option to increase the windmill size, like from 3 megawatt to maybe 6 or 7 megawatt?
Basically, when we just decided to design a power plant like a 20 megawatt, we decided that how we can choose the maximum efficiency of the wind turbine. So when we MATLAB simulation performed the here in for the 3 megawatt, our output is around 2.6, 2.5 megawatt for a specific one wind for 3. But when we perform this for a 5 megawatt, so our efficiency was low. So that's why we decided that we should move with the 3 megawatt. Any question? Okay, so next our presenter is the scaling theory for innovative piezoelectric energy harvested from atmospheric pressure temperature variations. Naveed Ahmed from Warsaw University of Technology, Poland. PhD student at the Institute of High Pressure Physics, Polish Academy of Sciences, and I am also working as a research assistant at the Warsaw University of Technology. So the topic I am going to present today is a piezoelectric harvesting device that can use daily atmospheric temperature and ambient pressure variations to generate electrical power. So first I will talk about why we need this harvester, because most of the IoT devices, they need require power of around 100 microjoules or less. So they are mostly the extension of the IoT devices are bottlenecked by this power giving the supply of the electrical power. The third one is I will talk about why the conventional energy harvesting techniques are good enough, but they have some limitations. So what is our idea and what is this mode of operation and how can we use this daily atmospheric temperature variations to power this IoT nodes. Then I will talk about the concept and topology and what the simulation tools are used and to get this the maximum power on 1 centimeter scale of this device. So product context, why we need this device that can power of low power electronics of 100 microjoules. So as you can see that the IoT devices are increasing with the passage of time, and now this time per capita IoT devices are 2.5, and you can see the total number is around 20 billion IoTs, sensor devices. So how they operate, they do not operate all the time. There is some portion where they can collect data and they require very less power, and when they transmit the data, the energy requirement is high, and then they just go idle. There is no operation and no power use. So we can use this portion just to collect the power, and then it's need we can supply them, and they can transmit the data and collect the data. So main idea is because these IoT devices they require power to use other sources of energy, we cannot be able to just drop and forget them. So this the main idea is just to drop this device and it needs to work all the time. So what is the bottleneck? So you can see that I told that this device needs around 100 microjoules of power. So remember, this is a IoT node. So if we charge it with the battery, it is expensive and it is very difficult to maintain batteries and power supply and the wires. And if we are using battery, we need to recharge them. And periodic replacement, then we have battery crash. You can see on this graph that almost half of the batteries that are wasted, only 50% of them are recycled, and other of them are just not good for the environment because they have toxic materials. So the idea is to have a such small harvester that can just paste on this IoT node and just can make the energy and just give it power directly without any wire or any support. So why not use existing energy harvesting technology that are using? So these are the most common energy harvesting technologies. You can see there's photovoltaic, rotational, mechanical, and thermoelectrics and radio frequency RF energy. So one of the main reasons is that for example, photovoltaic it is present in day, but it is not available at night. The vibration you need a constant vibrational source, and you need direct contact. It's same with the thermoelectric. There is a constant heat source needs to be there, and then one side should be cold and one side should be hot. So you need a constant contact. So RF frequency, it is you also need a source of it, and this source will be near to the harvester to get the power. So that is why there is all these harvesters need direct or indirect contact with the energy source. So what is the idea? The idea is to use the source available that is present everywhere and all the time, that is the daily atmospheric temperature variations. You can see that there are 3 cities in Poland that they have arranged from -2 to +4. Like you can say delta T is around 5 degrees centigrade. So we can use this to run this IoT. So this harvester, as it's small in size, it can be used for anywhere. So you can see for almost
everywhere there is a delta T is for 5 Kelvin. For Mars around 70 Kelvin, and on International Space Station it is around 300 Kelvin daily. And because it rotates every 90 minutes around the Earth, so we have 30x time that power. So where did this idea come from? So this idea came from the ECRES clock. It was invented by 400 years ago. It works on such a way that this valve here, it is filled with the chloroatom. This is a liquid that can evaporate around 12 degrees centigrade, so boiling point around 11 to 12 degrees centigrade. So even with 1 degree C, this can power this clock for 4 days. But this is only mechanical energy. So in order to convert that into microsize and into electronics, we need a innovation. So for that, this device can be useful. For example, this is a device that is a cavity which is covered with the piezoelectric membrane with top and bottom electrode to collect the charges, and then is a mechanical membrane. Then you can see when the liquid is inside, when the temperature increases, there is a vapor pressure increase. For chloroatom, it's only 11 degrees, which is very normal. So when the membrane is in bottom side, there is a negative peak. When it's flipped to the top side, it gives us a positive peak, so we can use this energy to get to chop IoT. So why chloroatom? Because chloroatom has a boiling point of 12 degrees C, around 11 to 12 degrees C, so it can be used for normal temperatures. For example, we check different liquids here with this glass metal. So you can see when there is a water, it gives us very less pressure, like 0.2 kilopascal per Kelvin is a propellant, and ethanol, but the chloroatom, you can see it gives us 1 degree C, which gives a pressure of around 4.39 kilopascal per Kelvin. So it is enough to flip the membrane from bistable. So what is the principle? So for example, if this device is simulated with the COMSO physics software, so the pressure is applied on the bottom side. So you can see when there is the membrane is in concave shape, and the pressure increases, the vapor pressure push the membrane upside, and when it gets into convex shape, you can see there is a jump in the membrane side. We need this sudden bifid behavior, not the linear one, just to push the charge to the capacitor or move on to the charge. So if the membrane moves linearly, it will not work. So we need a sudden jump, like bistable membrane, to get this power capture. So for piezoelectric materials, 4 different piezoelectric materials were tested. Which one gives the best performance? As the piezoelectric that D33 constant is a piezoelectric coefficient that tell us how much mechanical energy is converted into electrical. Also, you can see that the best one is PZT. So it gives us around 95 microjoules. Then there is ZNO, then PVDF, and then aluminum nitrate. Also, one thing needs to be remember that not only D33 doesn't matter. It also, the things that also depends on the conversion of mechanical to electrical is the dielectric properties and mechanical long quantities. So mechanical state is justified, the membrane rate will be very high and so the simulations were not for 3 different atmospheric conditions. So as we know that for Earth, around every place on Earth that has a temperature variation of around 5 degrees C. So you recalculate the pressure, and when the pressure is around 17 kilopascal, so we just flip to the other side and we can get 1.8 volts. And the size of the membrane can be same. We can just increase the thickness to we can use it in the other harsher environment where the temperature goes up, so we can have the thicker membrane, so it will flip according to that percentage. So the scaling is very important because we need to know how many membranes that can be fit on 1 centimeter scale are best enough to get the maximum power output. So we did the simulations. So you can see this is the simulations example how the simulation was done. So the size was increased from 0 to 64, and the maximum power we got around is when we have a device per centimeter scale, here we get around 200 microjoules with the double phase. So you can see that it is enough to power this IoT nodes that require 100 microjoules of power. So it can mechanical versatility is very important because it needs to boost output electrical energy, and the size of the material is around 300 micrometers, so it is not that big that can be used for the low power requirement. So the goal is this called is meta swing. So this is already done. So there is a microswing that is filled with the flow vacuum and it flips on the other side. So and the third one is the silicon that can be compatible with CMOS. So there is challenges here, and we're still working on this micro scale, and the simulations are done, and for these two we have already the results. So the conclusion is that if as the IoT market is expanding, so we need a solution for that. We cannot rely on wires and batteries. We need an innovative solution that will power them because they require very less amount of power. So for that, this device can be useful because it works always and everywhere without any contact of the source or without any orientation. Because temperature variations can be done inside the shades and outside, and it does not need any power source. So the main goal is to make this device a universal energy source that can work always and everywhere.
So any questions?
So actually, for the harvester systems,
Yeah.
okay, the energy or power can be very small amount, but the main point is that the energy density or power density. I mean, for a per volume or per mass, do you have a value for this power density or?
Actually, the power density depends on the deep 3T concept of piezoelectric material, and you see that there we have different materials. So the maximum power is around the PCT. So it can be different material, and this material give us the maximum power density. So I use this for the further calculations and simulations.
But you can have a value to compare with other systems that just get the meter cubic value per meter cubic value, this microjoule. So that can be very important to compare with other systems. Maybe in the external paper, please make this calculation. At least people can see which is better or moderate or lower power density. That can be a very good point of discussion.
Okay, I will make it available.
Okay, any question? Thank you. So our next presentation is by the Kiran Perkins, Northumbria University.
Good afternoon, everyone. My name is Mahdi Fanyanarchi. I'm assistant professor at Northumbria University from Newcastle. And Kiran Perkins is my PhD student, second year PhD student, and I'm presenting this work on his behalf. The title of this presentation is Large Eddy Simulation Artificial Neural Network Framework for Wake Prediction and Power Optimization of your tandem wind turbines under atmospheric boundary layer flows. First, an introduction of this project, this presentation. Well, currently, UK onshore wind target by 2030 is 29 gigawatts of power from 16 gigawatts currently producing. And the aim is to increase it 10 times by 2050, the global onshore wind capacity. And by the way, the main challenge, one of the main challenges in design of wind farms is power loss due to wake generation. Wake is the vorticity generated by upstream turbines that has impact on downstream turbines. So roughly around 40% of power is reduced and lost in tandem turbines. Tandem turbines means we have turbine upstream and the other one downstream. Okay. Well, there are several options in wind farm design. One of them is turbine spacing, spaced with wind turbines. And the other one is wake steering via yaw misalignment, changing the direction of turbines in right side or left side to change the direction towards the wind direction within the turbine. In this work, we use computational fluid dynamics, large eddy simulation coupled with actuator this method to resolve the physical properties of the turbines precisely, and also considering the ABL, atmospheric boundary layer effects. And the main challenge in simulation is that it requires lots of computation time, even on supercomputers. It requires roughly around 90 hours to simulate a single case of simulation. So it's far too expensive for optimization of a larger scale wind farm. The knowledge gap and our contribution is summarized in this slide. Prior machine learning models for wake prediction of wind farms, mainly focused on Reynolds average nominal Stokes data, which is a low fidelity model, very quick model. And it's not a high fidelity one. The other limitation in previous works was that they did not consider atmospheric boundary layer effects, which has huge impact on power production of wind turbines. Most of them use uniform inflows. And previous works mostly focus on wake field prediction alone without linking to power production optimization. In this work, we extend the primary large eddy simulation ANN framework with elevated realistic atmospheric boundary layer turbulence, training a wake field ANN across 4 turbine spacing, 3D, 5D, 7D, and 10D. This is turbine diameter. 3D is 3 times of turbine diameter, 5, 7, and 10 times. Diameter of turbine in this model is 126 meters. And we coupled it with a power ANN for full 0.1 degrees resolution of yaw angle optimization, and then validation every optimum case with CFD simulations. The numerical setup is summarized in this slide. The domain is 350 meter in X direction, 504 meter in the other side, and 630 meter in the Z direction. The number of nodes are provided here, and we use 2 benchmark turbines, horizontal axis wind turbines, and 5 megawatt, which are popular in validating simulations for wind turbines. And the diameter, as I said, is 126 meters. As you see, the main atmospheric flow hit the turbine. Rotational speed, the hop height of the turbine, and the domain is provided here. This is the first turbine, which is called upstream one, and the other one is downstream. The distance between them is variable from 3 times of diameter to 10 times of diameter. We use X-Compact 3D. It's a popular code developed in Imperial College. It's open source code and everyone can use it. It's basically for fluid flow simulations. One of the tools inside this code is for wind turbine modeling. The model was Smokorinsky. The computation cost is, we perform simulations on Archer 2 national supercomputer of the UK, 48 core HPC nodes, which require roughly around 90 hours per single simulation. For machine learning purposes, once we run the simulations, then we need to consider inputs and outputs and use that in training or model to predict the power in different scenarios. And we use two coupled neural networks. The first one is wave field ANN, and the other one is power ANN. This one is to predict the wave, the velocity profile, velocity contours in the downstream of the turbines, and the other one is for training and predicting the power production of these two turbines. The inputs are summarized here: x, y, upstream u angle, and output is local ux. U is air velocity in x direction. The model is summarized here. We use MATLAB software, MATLAB toolbox for the ANN work. In fact, my PhD student is working on that. This model is much faster than the simulations by itself. If we want to run every single case by simulation, it requires huge amount of time, which is the main limitation. But by using then training our model, it will be much faster. And the other side, we predict the power. Here, a summary of the training procedure. Training data by using 11 computational dynamic simulations per spacing. As I said, we tested our model for 4 different spacing: 3D, 7D, 5D, 7 and 10 times of diameter of turbines. So 4 cases, 11 simulation per case requires 44 simulations in total. We considered 4 of these simulations for interpolating and then sweeping for power ANN scans for different angles, and then validating the model with simulations. And also we perform sensitivity analysis to see how sensitive the turbines are to changing the angle to wind speed and the space between them, to find the optimum scenario for a real escape model. And here, on the left side, we perform a grid test to find the best element size for our model, the mesh number in millions, and the power generation for a single turbine are summarized here. As we see, for this element size 1.52, the power production roughly stays similar to a smaller element size, so we selected this element size for our model through the study. And on the right side, it shows a comparison of wave field ANN and simulations. In fact, machine learning comparison with CFD simulations. As you see, the simulations and machine learning are very similar. If you compare these two, are roughly the same. The red color is the wind speed hitting the first turbine. This is the first turbine, and this is the second one hitting that. And as you see, the angle is different from this one because we changed the angle to a different angle, 21 degrees, the angle. This is the upside view of our wind farm while selecting only 2 turbines as a sample for our model. And the error shows the maximum error is roughly around 4% comparison of simulation and training data in machine learning, which is a reasonably good error, acceptable error. Now, here it shows the maximum error, root mean square error, and mean averaging error, and R squared for different spacing of turbines. As you see, the maximum error is reasonably high, but it doesn't have impact on the results because these are for some isolated cases of those main simulations we perform. So it's not It's not a issue, it's not a challenge because it's isolated cases. And as you see, mean average error is very low, below 1%, which means that the simulation is working very well. Here, power production in ANN is summarized towards different view angles. As you see, for 3D, it's roughly a straight line, and training CFD, interpolating CFD, and optimum angles are used for plotting these graphs. The optimum angle for 3D is 26 degrees of view angle. For the other one is 30 degrees, 27 degrees for the other one, and 23.8 for the other case. The angles and their power improvement compared to the typical non-misalignments are compared. For 10D, the power production is improved by 14% compared to the original benchmark case. As I said, it's improved by 14%. For the other cases, the power production also improved. For the angle of 4.5 degrees, dash 5.8 degrees of angle. The power loss is summarized here for different cases. This is the sensitivity to see which case is more sensitive to our simulations. Here, CFD results are validated at the predicted optimum. As you see, total farm power in megawatt is compared between ANN and simulation CFD for 3, 5, 7, and 10D. The green one is ANN, the orange one is simulation. Most of them are very similar. Even in this case, both are roughly the same, 9.98% for ANN and 9.92% for CFD. Are very similar in 7D and a bit lower precision in 10, which is 1.87 percentage of difference. Here, wave-free accuracy is compared for different spacings. As you see, the error is very low. The prediction of power production in our model is accurate compared to simulations. And in conclusion, a validated path for large AD simulations, or LES, to real-time optimization was performed with my PhD student. The R square is very high, more than 0.99, much closer to 1 means more accurate model. Wave-field ANN accuracy at every spacing shows 99.9% of points, below 7% error. Power ANN means interpolating error across all 4 spacing, which is very low, less than 1%. And the other findings are summarized here. Future work, currently my student is working on a larger scale wind farm to optimize a wind farm located in Blythe area, close to Newcastle, to be able to model an actual realistic wind farm by the type of turbines they are using for this PhD work. Extend the model to full-scale wind farms, explore combined mirror and total tilt angle for onshore sites, and investigate denser training grids and additional aerial turbulence regimes. Thank you very much.
So, any question?
Shall we apply your methodology, this ANN methodology, to all kinds of, there are many types of wind turbines, worldwide. So can we apply this methodology, ANN methodology, to all of these turbines?
Well, this model can be applied mostly to onshore turbines, not the ones in the coastal area. Because in turbines located in seabeds, we have floating motions, we have lots of different parameters involved in. that has impact on power production of those turbines. But on the turbines located on onshore areas, not on land, particularly in flat areas, this model is very accurate and can predict the power very precisely. But on land, if we have different heights, for example, the turbine located at a higher height on the other one, different heights, then this model needs to be expanded and consider that parameter as well in power production of that wind farm.
So I have one question that you discussed the angle.
Yeah.
So I just want to understand what is this angle. This is the angle between when you are increasing the diameter of this one, or this is for specifically for one turbine?
Yeah. Well, as you see a turbine here,
Okay.
the angle is called yaw. We have different angles for a turbine.
Mhm.
One of them is yaw angle. As you see, yaw angle is provided here. Yaw angle means the turbine will rotate into left or right direction. Okay. So to change this angle, we have some sort of sensors inside the turbine, which is sensible to wind direction. Because wind turbine hitting the wind directly produce more power for us. So changing that angle is quite popular in design turbines. The other angle is tilt angle, that the turbine going up or down.
Yes.
So that's the
Okay. Thanks.
Thank you.
So this is for yes.
Yes.
Yes, perfect. Thank you.
And one for the this one last session. Yes.
And can we for one of this?
So our next presentation is sequential RDF pyrolysis with direct wet scrubbing, tide and use screening and closed loop water constraints. This is the author is Sergejis Osipovas from the Daugavpils University. Not present. So our next, not present. Fourth one, fourth session in fourth one.
Which one is that? We are in this one?
Yes.
Yeah, he's on here. Also, you change the chain. You can continue.
Okay.
Right.
So the next is the Kihao RWTH University.
Good afternoon, everyone, and my name is Kihao Ran. I come from RWTH Aachen from Germany, and I'm delighted to present my research result about the comparison between different technology for hydrogen production under different within the framework of a national supply chain. So following this guideline question, so I will answer through this presentation this question with if the competitiveness window for blue hydrogen is already closed for Germany. So before we really dive into the pathways, we have so many technologies that we can use to produce hydrogen. However, currently, which is proved to be upscalable and also to be really economic viable is blue hydrogen and green hydrogen. Blue hydrogen is based on the gray hydrogen with using the fossil fuel and feedstock without any decarbonization pathways, which dominates current hydrogen production pathway. And blue hydrogen with a really small ratio, just have using more and more carbon capture technologies to reduce the emission of the carbon dioxide. And the green hydrogen is parallelly, which was developed in the last decades through the electrolyzers and with alkaline or proton exchange membranes. Of course, there's some new technologies. As I said, it's economically viable. These are only the three. And why I only treat this another reason is because of the demands. Currently, most 100% of this demands is from the chemical and refinery industries. We see that for the transport sector and for other novel application like steel production, they only have nearly to 0%. And if we look at their demand, we see that is a huge demand compared to other small applications, which are all in the gigawatt power level. And so we really need to upscale production pathways. And here's a map of Germany, just an overview for you to locate where are these factories. Here are just some examples for that. And if we summarize this together, then we need something between them, which is a pipeline. Once we want to transport so huge or so massive amount of hydrogen, then we need the pipelines. We cannot transport through a car. The cost will be explosive. So if we analyze the former research, we find that neither of them really dive into the comparison between technologies in the level of supply chain. Most of them they stay at a facility like using techno-economic analysis, and some of them with small hydrogen clusters and analyze the viability of the hydrogen. And another factors affecting this national supply chain, of course, is the policy impacts and also many technology development. How far can this be developed in the future, and how efficient can it be? Therefore, in my research, I will put it very deeply with a very highly special and also temporal decision making with this core research question: how the technological parameters and policy designs impact hydrogen supply strategy for these hard-to-abate industries in Germany. And I just jump into the model. If we talk about pipelines, so different technologies, they require different pressures, and this is most cost of this transportation cost come because you need to compress it to a certain level for certain applications and also for certain usage. And like the salt carbon, they have the highest usage, and here is this model as one of the storage port for all the supplies. And also we have end users like refineries and chemicals, they have lower pressures. And of course we have this at the lowest level, we can produce a gray hydrogen production, which comes also is 1 bar through the steam mixer reforming. And also the traditional alkaline electrolyzers, because of water management, so it normally have a very low pressure. I think currently there are some research that try to pressure it up, but however the most used is with the atmosphere pressure level. And also the PEM electrolyzer, which delivers the 30 bars. And so we built one of the supply chain, and if we expand this to all the country in Germany, and then we will have this. Of course, there's many non-linearities in there, but because of time, I will not go deep into it. And beyond that, we know that German will or are planning to import, I think, at least 70% in the future for the hydrogen supply through the import pathway, because they don't have sufficient energy resources domestically. And so we need we need this portal as import to some of this at really high level through the overseas supply. And also the green hydrogen, this can be transferred or retrofitted to blue hydrogen production. Of course, it needs then we need to deal with this carbon dioxide to shift it somewhere like to Norway, and it was stored under the sea to avoid the greenhouse effect. So here is a summary of this model. Again, I will not go deep into it. You see that I also consider like the PEM and also and alkaline's aging, because if we have a time span like 20 years, and we need to take this stack cost into consideration, especially for PEM electrolyzer, the material for building it is quite rare, as elements are quite expensive. And now I will be focusing on the results, and I will show some interesting discussion and also the policy insights. First, in my model, I didn't only run it one time. I run it with this scenarios design. First, we varied CO2 price and carbon capture efficiency to simulate how the future policy and technology development could be. And beyond that, also for the CCS downstream cost level with only 3 levels, but it is not that detailed model, because this research is about hydrogen. So and carbon capture and storage is also a long downstream supply chain. So I put it just as a package here. And beyond that, there's an interesting analysis is about that the German government only wants a blue hydrogen. Blue hydrogen is also fossil fuel based hydrogen, and they only want this as one of the bridging technologies. Bridging technology means means they need to exit, or they need to phase it out one day in the future. So then comes blue hydrogen exit regulation. If there will be no regulation or mandatory, or give companies compensation to let them close their own factories using the fossil fuels. And of course, I will show one example. We take one of the middle CO2 price and carbon capture efficiency, and we see how it differs between different CCS downstream costs and also the exit regulations. And here is one of the results. And first we see at the diagram, you see, and the y-axis, it is all about the annual supplies of hydrogen, which I wrote it in terawatt hours. Don't be surprised that this is all constant, because I assume all the demands are constant through years, because all the chemical and also refinery plants they want to run at unchanged operations to minimize the cost. And on the X level, which is year, which is easy to understand, and we see different color in it, which is run which is run in an optimization model, and we see that what is optimized when they choose. And first we see that the green hydrogen, which is not favored, and it is almost completely exit at 2033. Maybe it is because of the high carbon price for the green hydrogen. It emits too much CO2. And green hydrogen, we see it reach the roof of the resources for Germany really, really fastly. Also at about 2030, and it hits the roof, and then it keeps unchanged. So the rest of the part, mostly, if we don't set any exit policies, the company will keep using the blue hydrogen because of the cost competitiveness. And if we give them a compulsory exit for blue hydrogen, which means from this year, which this line showed that afterwards no companies are allowed to use blue hydrogen, and then they have to switch to importing hydrogen. So now the question comes out, we need to focusing on the blue and import hydrogen because as a constraint of renewable resources in Germany, we constantly need to import or we produce hydrogens in our own way. Otherwise, there is also another explanation: should we import natural gas or should we import hydrogen? That is the implication from this report. And let's see another result, which we varied all the CO2 price and also carbon capture efficiency, but we fix the policies. We just fix the carbon, the CCS downstream costs, and also the regulations. And then we can draw a phase map. So from there's 4 diagram, and the y-axis is efficiency. So we change from the 55% to the 90%, which is from the low capture efficiency and to the very high one. And the x-axis shows the carbon price. We varied from 50 euro to 450, which is really high. And the color shows how much percentage is the blue hydrogen is deployed and how much import hydrogen is conducted. So this is a natural sequence what we can do after we figure out, okay, the question that's between the blue and importing hydrogen. So we see that the result, if we increase the carbon price and also we reduce the achievable carbon capture efficiency, we will come to the corner with nearly to white, which means the blue hydrogen will be punished by the CO2 price, and then we need to switch to the import. And naturally, if we have a really high carbon capture efficiency, then we will see that blue hydrogen shows and dominance against importing hydrogen. And why I show another 2 figures? These shows that the operational cost for one of these scenarios, and we see that if we switch, if we mandatorily close the blue hydrogen, we will dramatically increase the cost, nearly at 50%, to 28%, and this is incredibly high because we almost double. You see that because if we import the natural gas, then we will have the blue hydrogen gas feedstock and also the almost double height of this import hydrogen. So this shows the cost ratios. And if we think of the current situation in Germany, and we are at this level, we are at the current carbon price at nearly about 90 euro. So as said here, it's between 75 and 100 euro. And so we also see that there is a slight differences in this capture. So, but if we really want to reach something, we need to increase our carbon price into an unbelievable high level. So it is almost not acceptable by any of these industries. So that's another result we can derive from these figures. So let's summarize this page. So the natural gas feedstock plays an essential role, especially in the bridging phase for the blue hydrogen, and also the mandatory only shifts the market from importing natural gas to importing hydrogen without solving any energy independency problem, and also increase the cost dramatically. Maybe you have a question on the investment locking, why I use the operational cost. Because if we look at the investment cost, which is compared to the operational cost, which is much lower, the reason is because that current refineries, they already have all the facilities there. They only need to retrofit their facilities and also their devices to carbon capture processes. And if we look at this, we can also gather some insights from it. First, if we have a low carbon price, then then we will get early transition from gray to blue because the carbon price doesn't only surprise the gray hydrogen, it supplies blue hydrogen at the same time. And under this investment of the CCS, we also see that the OPEX dominates, and high CCS technology can make the company more resistant to the carbon prices. So the key takeaway here is that investment lock-in does not come from the investment, but it's mostly based on the operational cost. So let's give a short conclusion and outlook. First, we developed this model, which is a national end-to-end supply chain model, which starts from the production through the transportation to the end. And we also compare different hydrogen production pathways at the supply chain level. And we take different technologies and policy-driven exit parameters into consideration. In the future, we can take more. And also explicit consideration of this special and temporal hydrogen production conditions. Because of the lesser data, we can only be specific to the monthly accuracy. And also about the managerial contribution, we find that okay, the shift from the blue hydrogen to import will significantly increase the cost, and it doesn't solve the problem that currently Germany face. That's important is a import dependency. And hydrogen import remains still, but in the future, a key supply methodology. And this hard policy exit regulation, which like in past years, the coal exit cannot solve the problem of the hydrogen viability. However, this research also, of course, have limitations and outlooks. First, we need to specifically analyze some more policy parameter which is used in the reality, like the offtake agreement. For example, if we give some constraints between this book and claim, for example, I buy from the south and someone use it from the north, is that eligible? And which subject to some temporal and regional variabilities, and then we can give more concrete policy recommendations. And the second is, of course, that Germany is one country in the EU, so it is naturally if we can expand this geographical reach to the European hydrogen backbone, and then we need to extend the timeline a little bit later because the infrastructure building in other countries is a little bit slower compared to Germany currently. And the last one is the most interesting one is that about the coordination problem, because in this national supply chain, different sites, they have different interests, so they will decide on their own. They will not accept to make some losses, because in the optimization model, you are like a really high-level planner, so you will assign some sites to make profits, some sites to make losses. So if we can solve this coordination problem, so we will introduce some maybe machine learning using reinforcement learning method to solve it. And that's all, and thank you for your attention, and I'm looking forward to your questions.
So any question?
Thank you very much for the presentation. And according to what you explained, the blue hydrogen route is not viable now because of the price of hydrogen and carbon is not comparable with the cost of the production, right? And you say that you cannot increase the price because the market does not tolerate that. How about, what do you think of the role of technology in reducing the cost? I know for blue hydrogen, for example, for hydrogen production, the stable forming of ATR are mature technologies. You cannot do anything about that. But how about the carbon capture, for example, the different types of absorption, this kind of thing, to reduce the cost?
Yes, I think this is a really interesting question. At the really beginning, of this research, I do change this part because now we don't have the carbon capture that can be scaled from the 55% to the 90%. Now what we really have is only two options: it's 90% and 55%, but with a different investment and also operational cost, which really differs. So, so if the technology development really can improve this result, then we will have that, then we can put it here. So at this stage, it is true I cannot analyze it because I looked up of many blue hydrogen paper and also from the laboratorial level, they also claim that some of this cost, but they don't have a how to say, evidence that it is really 100% or at least from the 90% confidence to say that it is usable. That's why I screened this. I want to show, for example, if we reach 70% in the future, what will happen? If we reach 100%, 90%, what will happen? Yeah, and this is same for the CCS cost. And this is actually modeled from the Germany, and with a trailer to transport the CO2 to the Hamburg and transport through ship to Norway. So, for example, in future, if we have a carbon pipeline, which will be much cheaper, because this level is incredibly high, 75 adds on the carbon price. So that's the answer. Yeah. Thank you.
So I have a question about this, that on what parameters you calculate the CO2 price? And second question is that when you are calculating the CO2 price, do you consider the LCA study for a specific hydrogen production method or not?
Yes, this carbon, you mean the emission CO2? Yeah, the emission CO2 come from a literature that from Neuwirth in 2022. So it's quite a little bit old, but it considers the CO2 from all this green hydrogen currently, which comes out at 13 kilograms CO2 per ton of hydrogen. And here, yes, and it's interesting because here is one point that I forgot to mention. Because in his model, it also calculates the upstream.
Yes,
because
upstream.
if you gather natural gas from the earth, then you will have the upstream leakage. And I just put the parameters here in the model, but it is fixed because this value is depend on the import source. For example, if you import from Russia, you import from US and from the Middle East, which the value will be different.
So for this whole study, you just consider it by the methane reforming or something methanol hydrogen production, or only one you consider parameter?
Yes, this is one parameter.
Okay.
Yeah, this is one parameter for green hydrogen.
And for one parameter like methane steam reforming,
yes,
you did not consider the LCA study, life cycle assessment of this whole process.
No, I didn't conduct the LCA study. I took the results from other LCA study.
Okay.
Yeah.
Okay. Thank you so much. So now we are moving towards the last presentation of our session, and this is the experimental and parametric analysis of a solar-driven desalination system for sustainable water production.
Thank you, Mr. Sugest. Good afternoon, everyone. It's a pleasure to be here today. My name is Fatima Aidnouh. I am a professor at the Polydisciplinary Faculty and Research Associate National Center for Studies and Research in Water and Energy, Marrakesh, Kadi Ayad University, Morocco. I am honored to present our work entitled Experimental and Parametric Analysis of a Solar Driving Desalination System for Sustainable Water Production. This work conducted in collaboration between Kadi Ayad University, Morocco, and Université Lorraine, France, and the University of Gabs, Tunisia. Allow me to describe the structure of our research. I will beginning with an introduction, and I present some problems related to water scarcity and the solution. Then I will move into the experimental part where I will present our experimental setup and our results. Finally, I will end with a conclusion. As we know, water covers most of the Earth's surface. Less than 1% of it is accessible fresh water. Water scarcity is expected to worsen, particularly in Morocco and the Maghreb region, which could lead to a severe water crisis by 2030. Consequently, the development of sustainable freshwater production technology is essential to address this water crisis. The main alternative for solving the growing shortage of fresh water is seawater desalination technology. So, what's the desalination? Desalination is the process of removing dissolved salts and other impurities from seawater or brackish water to produce fresh water suitable for drinking, agriculture, and industrial application. There are several desalination processes, such as electrochemical, membrane, crystallization, as well as evaporation and condensation, that is being among the initial methods introduced for freshwater production. Our systems operate by harness direct solar energy for desalination. Pardon? That's why our work focuses on developing an autonomous, low-cost, and eco-friendly system capable of desalinating seawater and brackish water. This system aims to provide a reliable water supply while minimizing environmental impact, offering a practical response to the growing water scarcity in our region. We will now describe our desalination system and the method used. Our solar desalination system is installed at National Center for Studies and Research in Water and Energy at Qadi Ayyad University, Marrakech, Morocco. The system consists of a solar dish, a steel, and a condenser. This solar dish, named Schiffler, functions as a stationary solar radiation concentrator. It uses a primary reflector to direct sunlight to a secondary reflector, which then redirects the concentrated beam to the base of the desalination steel. The primary reflector is a motorized solar tracking parabolic dish that conditionally follows the sun, directing solar radiation toward the secondary reflector while maintaining the focal point. The secondary reflector, composed of 6 aluminum stibs, redirect the sunlight reflected by the primary reflector to the circular base of the solar stib. The alembic is the main vessel containing the brackish or seawater to be distilled. It is equipped with a pressure gauge and a temperature indicator to monitoring the operating condition. The condenser, a water-cooled coil condenser, is used consisting of a steel coil enclosed within a cylindrical stainless steel casing. The solar concentrator captures and focuses sunlight to heat the water into alembic. As the water heats up, it evaporates, leaving salts and impurities behind. The water vapor travels through the pipes to the condenser, where it cools and condenses back into fresh water. The system is monitoring using a pyranometer, a weather station, K-type thermocouples, and an Arduino-based data acquisition system to measure solar radiation, temperature, and condenser performance in real time. The meteorological conditions were analyzed before the experiment. Figure 1 shows that both solar radiation and ambient temperature increase from morning to afternoon, and then this decrease towards sunset. Peak solar radiation and ambient temperature were observed in June 1st, 2023, reaching approximately on 1,050 watt per square meter and 33 to 34 degrees Celsius. Respectively, in contrast, the lowest values occurred in January 1st, 2023 at approximately 1,620 watt per square meter and 27 to 28 degrees Celsius, respectively. The similar trends demonstrate a strong correlation between solar radiation and ambient temperature, providing favorable conditions for efficiency solar desalination. To assess the impact of solar radiation on production, we measured the temperature variation inside the distilled water still every 15 minutes. These figures show that the temperature in the water inside the still increased with solar radiation, but the variability of this radiation makes it difficult to reach the evaporation. Temperature in June, evaporation temperature is reached more quickly due to higher solar radiation, which has a direct impact on distilled water production. Present experimental results on the productivity of solar steel on days with favorable weather conditions. We plotted variation in water temperature and solar radiation over the courses of an experimental days with average radiation of 860 watts per square meter. It can be seen that solar radiation increases progressively over the course of the day, influencing freshwater productivity. Next, we studied the influence of cooling water and the condenser level. The table shows that distilled water production is influenced by both solar radiation and the inlet temperature of the high transfer fluid. Altitude production generally increases with solar radiation. A decrease is observed at 883 watts per square meter compared to 792 watts per square meter, confirming that radiation is not only determining factor. Although high transfer fluid and inlet temperature improves the heat transfer, promotes condensation and thus increases distilled water production. This section evaluated the effect of the initial water volume in production by testing for volumes 15 to 20, 25 and 30 liters under identical condition over 4 days. The results show that production decreases as the water volume increases due to a longer heating time before evaporation occurs. The highest yield was obtained with an initial volume of 20 liters. At the beginning, high conductivity values were observed indicating high salinity. Then the conductivity decreased approximately to around 3 microsiemens per centimeter, which correspond to very low salinity. These results confirm that the produced water is distilled water and demonstrating the good performance of the system. System efficiency is calculated using the following equation. This table shows the results for 3 different dyes with different solar irradiation. So, for an irradiance of 814 watts per square meter, the system yield is maximum. In conclusion, our study of distilled water production using a solar concentrator demonstrated the importance of several parameters in achieving optimum performance. Under optimal condition, we achieved an efficiency of 28.65%, produce 9 liters per day of distilled water with an electrical conductivity of 3.4 microsiemens per centimeter at an irradiance of 870 watts per square meter. The system's high productivity was maintained by keeping the temperature of the cooling system between 99 and 35 under good climatic conditions. Environmental analysis also revealed a net reduction in CO2. For more information, this work has been published in the journal Energy for Sustainable Development. And thank you for attention.
Thank you, Professor. So, any question? No? Thank you, sir. Now we are moving towards the another session.
Actually, now we have company.
Yes.
There is tea, coffee, and fresh water. Just you two so much mechanical engineering. It is a
Yeah, thanks so much. Thank you.
شكرا جزيلا.